Here we go with 5.08. Just a quick reminder, if you are watching this, to make sure this is the video you actually want to watch. Juniors, you probably want to back up a couple to make sure that you're on the correct one. All right, so today we're going to write an exponential function to model a verbal description of a context. So we've done a lot of work looking at how exponential functions are graphed, understanding why they are graphed the way they are, and we've looked at some real-world situations where we're given a graph or we're given a function, and we explain something about that real-life situation given that function. Now we're going to take it up one notch, and we're going to actually write an exponential function based on just the description of the situation. So you tell me the relationship with words, and we're going to be able to create a function that models that situation. So this can seem confusing to a lot of people, but you guys should be in great shape because we've already talked so much about how the different pieces of an exponential function will change the value of the function itself. To start off, let's take a look at the real-life situation where we were given a function, and we'll really focus on how each piece of this function contributes to what the situation is actually doing. So the soda is sitting in a warm room, and the temperature after t minutes is given by this equation, 75 minus 35 times e to the negative 2t. And our goal is to sketch a function and use it, sketch a graph of the function and use it to make a prediction. So before getting started, I want you to pause and remind yourself again what you expect to be happening to the temperature of the soda as time moves onward, and be as precise as you possibly can. Hopefully what you said to yourself is, okay, the soda's cold, it's in a warm room, I expect it to get warmer and warmer and warmer until it finally reaches the room temperature. Okay, that seems to make sense, right? If you were to leave a soda in a warm room for a long time, that's probably what would happen. So when we are graphing eventually, and we're looking at what happens as time increases to the temperature, we expect that it's going to start somewhere and it's going to increase, right? The temperature is going to get bigger. Now the question is, how is it going to increase? So in order to look at that, let's analyze our function and try and sketch a graph of it so that we can better understand what's going on. First thing to notice is that we have an exponential 35 times e to the negative 2t. And as I always want to do, if I have a negative exponent, well, I'm better at working with positive exponents. Those are much easier to understand. So instead, let's write this in a positive exponent form as 1 over e to the 2t. And now I can put this into a much easier to recognize form by applying the exponent to the numerator 1, because 1 to any value raised to any power is going to be 1. So go ahead and do that, and once you've done that, I want you to think about how you would graph this function and maybe give it a try just to start off. All right, so notice that I'm going to apply this exponent 2t to the numerator as well. And so what I'm now going to have, and I'm going to move this over here, is I'm going to have f of t is equal to 75 minus 35 times 1 over e to the 2t. Okay? Now, at this point, we can actually sketch the graph of our function. There might be one more step that you might want to take, but at this point, you can do it. So think about what's happening. You have 75, and you're subtracting from it 35 times 1 over e to the 2t. Right? This is an exponential. How will this exponential behave? Think about it. Well, 1 over e is a number less than 1, greater than 0 but less than 1. And so when I raise it to bigger and bigger powers, this whole value is going to get smaller and smaller. So when I take 75 and subtract values that are getting smaller and smaller, I see that I'm going to be getting closer and closer to 75, which makes me think that my function is going to have a maximum value of 75, right? It should never pass 75. So what we want to think about is that our temperature is going to start at some initial value, and it's going to, as we talked about earlier, the temperature is going to increase, right? And it's going to increase and increase and increase and increase, but it's not going to ever pass 75. Why? Because I have a number less than 1 being raised to a bigger and bigger power, so that's going to make this value smaller and smaller, but it's never going to quite be 0. So I pretty much have it here, and what I need to do now is actually figure out my initial value. So the initial value is when t is 0, so f of 0, well I can actually do this in my head, it's 75 minus 35 times 1 over e to the 0, and that's going to be 1. So 75 minus 35 leaves me at 40. So here's my initial value, here's my initial point, my y-intercept, and now I should be able to figure out, well, it can't be moving in a straight line, right? That would be a linear function. This is not a linear function, this is an exponential function where the b value is less than 1. So when the b value is less than 1, remember, does that mean our average rate of change, are we getting steeper and steeper, or are we going to get shallower and shallower? And what it means, of course, is that our values are going to get shallower and shallower because the more times I multiply by a number less than 1, the smaller the changes I'm going to make. So I could go ahead and sketch my graph, and it would look like that. But you may still be a little skeptical. Why is it that my function looks like this? And I want to show you one more way to write this function. So let me give you an example. If you have the number 10 minus 5, this is the same as switching these around and writing negative 5 plus 10, right? Either way, you're going to get 5. So why is this helpful? Well, remember that when we started out this unit, we were writing exponential functions with a times b raised to the t plus some c value, and our c value was telling us how big our translation up or down was going to be. Well, this can allow me to write my exponential term first and then the constant term second. So I can write this as negative 35 times 1 over e to the 2t plus 75. And here, what we can realize is that, oh, yes, we have a function that should look like this. And how do I know it'll look like that? Well, I can just go through and I can go back into my notes if I need to and remind myself how to sketch a function like this. Remember, of course, that this negative out front, that changes everything that was positive into a negative. So if I first just consider this piece here without the negative, what I'm realizing is that this is a function. When t is 0, it's going to have a value of positive 35, and since the b value is less than 1 but greater than 0, it's going to decrease and get shallower and shallower. But the negative out front reflects this over the x-axis, so now this point's going to come down here, it's going to be negative, and it's going to move upward like that. And then the last piece of the equation is that I am adding 75, which translates my function upwards 75 units. So this initial value point, which seems to be at negative 35 now, is going to shift upwards 75 units to 40. This, which was approaching 0, that's going to shift up 75 units, and it's now going to approach 75. So either way, I can sketch a graph of my function that looks just like that. So the only remaining question then, of course, is when do you predict that your temperature is going to reach 70 degrees Fahrenheit? And if you look at our graph here, right, we might be able to make a prediction. Maybe we think 70 is right about here. Maybe we think it's right about there. But we still, right, we need to make a much more precise graph. We need to plot a lot more points to make a really accurate prediction. So while this gives us a basic idea of what's going on, we're going to need a better method to make a very, very accurate prediction. All right, we're going to start with a very simple question that is going to allow us to then kind of springboard forward and write a lot of more complex functions. So you have $12 and you want to double this amount every month. Write a function f of t to model the amount of money you will have after t months. So pause the video, try this on your own first. It's important that you think about how this will work. Maybe create a table, take a look at how the values are changing, think about what your function will look like. Give it a try, and then we'll take a look. All right, so I've just sketched out the first couple of sequences here. At the very beginning, 0 months have passed, you've got $12. 1 month goes by, and now you have 24. So how did you get 24? Well, you took 12 and you multiplied it by 2. You doubled it. Okay, and then the next month, you doubled that again. So how did you get 48? Well, you took what you had before, 12 times 2, and you doubled it. In other words, you multiplied by 2. And then you got 296 by doubling that. So you had 12 times 2 times 2, that's the 48, and then you multiplied by 2 again. So we can see that at each step of the way, we are multiplying by another 2. And this should give you a hint as to what the pattern is. I want to multiply by the certain number of 2's that will allow me to double my initial value that many times. So after 1 month, I'll double it once. After 2 months, I'll have doubled it once and twice. After 3 months, I'll have doubled it once, twice, 3 times. So to double something once, you multiply it by 2. To double something twice, you multiply it by 2 times 2, which is 2 squared. To double something 3 times, you multiply it by 2, and by 2 again, and that's 2 to the third. So, what is my function going to be? Well, f of t is going to take my value 12, and it's going to multiply it by 2 a certain number of times. Well, after 1 month, I want to multiply it by 1, 2. After 2 months, I want to have multiplied it by 2. And after 3 months, I want to have multiplied it by 3 2's. In other words, 2 to the t. And now I should be able to see how this works, right? I have some initial value that I'm starting with, right? When t is 0, that's just 12. And then every time t increases by 1, I am doubling it or multiplying by another 2. So we could check this out. You could plug in these values and see that you will end up getting all of the correct values. All right, so now let's switch it up. Doubling your money is really impressive, right? Doubling your money means that you are increasing the amount that you have each month by 100%, right? First month you have, after 0 months, at the beginning you have 12, and then you've doubled it, meaning that you've added on another 12, and that is 100% of what you started with. So you added 100% to your total. Here, let's think about if instead you want to increase your money by only 50% each month, how will your function change? So think about it. Go ahead and try writing it down on your own, and then we'll talk briefly. All right. For us to understand what we're going to do when we increase by 50% each month, I want us to go back and remember that when we're doubling, we are increasing by 100% each month. And the way that you can see that is if I take some value like 12 and I multiply it by 1 plus 1. When I distribute, notice that 1 plus 1 is of course 2. When I distribute the 12, notice that multiplying the 12 by 1 is going to retain the original 100%, and that multiplying by the next one is going to add the additional 100%. So if I'm thinking about increasing my amount by 50%, what I might want to consider is if I have $12 and I want to increase by 50%, I'm going to need to multiply by 1 to keep the original 100% because I'm increasing by 50%. And then I need to add on 50%. Well, 50% is 1/2 or 0.5 of 12. So this value will now be 0.5. So the new method, what this really is for 50% is that I'm going to have 12 times 1.5. And when I multiply by 1.5, that's going to increase whatever my value is by 50%. So when I look back at my table of values, instead of doubling, instead of multiplying by 2, to increase by 50%, I'm going to multiply by 1.5. So I'll multiply by 1.5 instead of 2, which leads me to my function f of t being 12 times 1.5 to the t. Because now, every month, I'm going to add 50%. In other words, I'm going to multiply by 1.5. So after the first month, I'll have multiplied by 1.5. Then, over the next month, my money is going to increase by another 50%. So I'm going to take whatever that was and multiply it by another 1.5. So to think of it this way, in month 0, I have 12. In month 1, I'm going to have 12 times 1.5. In month 2, I'm going to have this 12 times 1.5, this amount here, and I'm going to multiply it again by another 1.5, which is 1.5 squared. And so I notice that I'm simply multiplying by 1.5 every time, and that's going to be 1.5 to the t, an exponential function. All right, hopefully that went well. I'm going to give you 2 problems to practice so that when we arrive tomorrow, we can look at some different options. We have 3 different countries, the US, Canada, and Mexico, and some information about how their population is increasing. US by 1% every year, Canada by losing 10% every year, and the Mexican population is increasing by 3.5% every 4 years. And you're going to write 3 functions, each one to model a population of one of the countries in terms of t years. And you can look up the current population if you need to. Okay? So you need to write out 3 different functions. And what I want you to do is in your comment, you need to post the function that you are going to use for Canada. So let's just call that C of t for Canada. That needs to be a function that you post in your comment. All right, so I'm going to look for all of these in your notes, but post your function Canada in the comments, and also a question that you have or an answer to someone else's question.